Last week we started on public key cryptography and we started going through the example of RSA. We skipped over some slides. So at the start today we're going to go back and recover those slides we skipped and then return to RSA and work through on the board that example of how RSA works. But first let's go back on general about public key cryptography. As opposed to symmetric key cryptography, we have two different keys and we encrypt with one of those keys and we can only successfully decrypt with the other one of the pair of keys. So the two keys need to be related some way. It depends upon the algorithm. RSA is one algorithm for public key cryptography. There are others, but the two keys are related in some way such that encrypt with one, you can only successfully decrypt with the other. And sometimes vice versa. That is, you encrypt the other one, you can only successfully decrypt with the original. If you try to decrypt with a different key, one that is not one of the pair, then you'll get garbage out. That is, you'll detect that it did not work. It's the same as trying to decrypt something encrypted with DES with the wrong key. You'll not get the correct ciphertext, plain text back. So there's two ways in general that we can use public key cryptography. We can use it for secrecy or confidentiality. I want to send a message to someone and I don't want anyone else to be able to read that message except the recipient. So what I do is I use a public key algorithm and a pair of keys which are generated in some way, and I encrypt with the destination's public key. The public key of B in this case. I encrypt with their public key, send the ciphertext to them, they decrypt with their private key and get the original plaintext back. And if the algorithm works and the keys are chosen correctly, it should be hard for the attacker, given the ciphertext, to be able to decrypt that ciphertext and get the original plaintext. Because they don't know the private key, they should not be able to decrypt and get the original plaintext. And similar, it should be hard for the attacker to, given the public key, find the private key. Because once they find the private key, then they've defeated the system. It's no longer private. So that's the model for confidentiality. Encrypt with the destination's public key. Only for confidentiality, that service. The other mode or the other way that we can use public key cryptography, and is often used, is for authentication, trying to make sure that the person sending the message is who they say they are. And the way that we use that is that the source encrypts some message with their private key, sends it to a recipient. The recipient needs to validate the message that they received. They need to check somehow. I've received a message that it says it's from A. How am I sure that it is from A? Well, to be sure, they decrypt with A's public key. Because the nature of our algorithm should be that if something's encrypted with the private key, it can only be decrypted with the corresponding public key. So if it's encrypted with the private key of A, and it successfully decrypts with the public key of A, then B knows it was encrypted with the private key of A, and therefore B knows that A sent that, because only A has the private key. If the malicious user tries to pretend to be A, then they need to encrypt the message with some value. They cannot encrypt with the private key of A. Let's say I'm the malicious user, I encrypt it with my own private key, the private key for Steve. I send it to B, pretending to be A. If B receives it to check that it came from A, they'll decrypt with the public key of A. But it was encrypted with the private key of Steve. It will not successfully decrypt with the public key of A, and therefore the recipient will detect that something's gone wrong. So that provides authentication. It doesn't provide confidentiality. The attacker can still see the contents of the message. That's not the objective here. It's just to provide authentication. Of course, we can combine the two together. If we want both authentication and secrecy, we can combine those two operations as shown in this illustration. Encrypt with a private key of the source, and then encrypt with a public key of the destination for confidentiality, and that should provide both services. So that's how public key cryptography can be used in general. Where is it used in practice? What are some of the applications? Well, secrecy or confidentiality, encryption and decryption of messages. That's one application. Digital signatures, sign a message. When I have a document, a piece of paper, and I sign my name on it, and I give that piece of paper to someone, then my signature is considered some form of authentication. When you have that piece of paper, because it's my signature and my signature only, that confirms that I agree to that document, or I've read that document. When we're communicating across computer networks, we want the same form of security service to be sure that someone delivered that message or are aware of that content. They sign a message. And we use the authentication mode of public key cryptography. If you encrypt with your private key, it's only you have your private key. It's the same as signing something with your signature. Only you have your signature, assuming no one else can copy your signature in that case. So digital signature is a common application of public key cryptography. And another application is key exchange. When we use symmetric key cryptography, one of our problems is that I need a secret key and I need to exchange that with the person I want to communicate with. Exchanging secrets is not easy over a network. We can use public key cryptography to exchange secrets. So that's one application. Some algorithms. RSA is one algorithm for public key cryptography. There are others based on different mathematical concepts, elliptic curve algorithms, Diffie-Hellman, DSS. So these are just 4 examples of algorithms and their use in these 3 different applications. Yep.
How do we actually exchange the key?
In symmetric key cryptography or in public key cryptography, how do we exchange the key? Easy. If I have a public key, I generate my own pair of keys. My public key, my private key. My private key I keep private. My public key I tell everyone. I post it on a website. I send it in an email. It doesn't matter because it's public. And we'll see, and be after the midterm, that there are some algorithms for do that automatically across a network.
What about symmetric?
In symmetric key, if you and I want to communicate, we both need the same key. How do I give it to you? I cannot post it on my website because everyone else will see it. I cannot include it in an email. We need to use either some other communications channel. Write it on a piece of paper, give it to you. Or send it to you encrypted using public key cryptography. So we need some other way to do it. That's the problem. We have an entire topic on that after the midterm. So these different algorithms can be used or are applicable in the 3 different applications. RSA could be used in all 3 of them. Diffie-Hellman, for example, is only used for key exchange. It's not used for encrypting data, for confidentiality, not used for signatures. It's built just for key exchange. DSS is built just for digital signatures. We're going to go through today RSA, and also we'll get on to Diffie-Hellman, just as 2 examples of public key cryptography algorithms, and popular ones. Still on the general algorithms, what do we require of our algorithms? and the keys that they generate. Some requirements include that it must be easy to generate a pair of keys. That is, every user needs a pair of keys. Therefore, we need some way to generate them. When we say easy or computationally easy, it means that we can do that in a short amount of time with a computer. Computationally hard means it will take practically forever to do it. So, to make it easy to use and practical to use, then we need to have algorithms such that it's easy to calculate and generate a pair of keys. So that any one of us can run some software and within a few seconds get our own public and private key. You can, for example, use OpenSSL to do that. It should be easy for A, say the source, knowing the public key of the destination B, to do encryption to generate the ciphertext. That is, I have some plain text, M, I have the public key. We need an algorithm such that it's computationally easy to do the encryption. That is, if I have the plain text and a key, it takes seconds at most to do the encryption, maybe minutes in some extreme cases. I don't want it to take hours, days, months, years to encrypt something. It's just not practical. And similar from the other receiver's perspective. It should be easy to decrypt something if you have the correct key. If something is encrypted with public key of B, then B should be able to easily decrypt it as they know the private key of B. So the encryption operation should be computationally easy, as should the decryption operation. That's to make the algorithm practical, these requirements must be met. Now, about the security of the algorithm. It should be computationally hard or infeasible, practically impossible for an attacker, if they know the public key and C, the ciphertext, should be practically impossible to find the private key B. Because if they can find the private key, then it's no longer private and that the attacker can decrypt. So that's a security requirement. Hard to find the private key given the public information. And the public information is the public key and the ciphertext. And hard to find the plaintext given the public information. You know the public key, you know the ciphertext, it should be computationally infeasible to find the plaintext M. There are two security requirements that we need for our algorithms, so that we need to choose an algorithm that meets these requirements. As an optional requirement, it's not needed, but sometimes some algorithms have this or meet this requirement, we could apply the keys in opposite orders. That is, we've said here, if we encrypt with a public key, we can decrypt with the corresponding private key. But it would be nice sometimes to do it in the other way. If we encrypt with the private key, we can easily decrypt with the corresponding public key. That's what this says. That we can use them in any order. Some algorithms have that requirement or meet that requirement, others don't. We saw when we looked at confidentiality and authentication, that's basically what they do. They swap the order in which the keys are used. So requirements 4 and 5 are for security. 1, 2 and 3 make the algorithm or the approach practically easy to use. And requirement 6, which is optional, is useful if we want to use the same algorithm for both confidentiality and authentication. We'll see that RSA does that. So, those requirements, what algorithm or what function meets those requirements? What is this algorithm or function E that takes some public key in M and can calculate C easily, but given C and given the public key, it should be hard to get M. If you look at this function and requirement 5, it should be easy to go in this direction, but hard, given this and the public key, to find M, to do the inverse, essentially. We need some algorithm or function that meets that requirement. And such a function is called a trapdoor one-way function. Let's look at the requirements of such a function, or the characteristics. Such a function, every value has a unique inverse. So we need to be able to find an inverse to go backwards. We need a function that going in one direction is easy. Calculating the function is easy, but calculating the inverse is hard. That's what we need, a one-way function. It's hard unless we know some certain information. So, we need some function f that takes as an input k, operates on some input x, and easy to find y. So easy to calculate the function in one direction, if k and y are known. Also, if we know some k and y, it should be easy to do the inverse. This is really relating to these two requirements. We need a function that it's easy to encrypt if we know the public key and M, and it's easy to decrypt, that is the inverse operation, if we know the private key and the ciphertext. But it should be hard to do the inverse if we don't know k. If we know y, it should be hard to do the inverse. If we know the ciphertext, it should be hard to find the plain text if we don't know the private key to do the inverse operation. So that's our general requirement of such a function that we need to use for public key cryptography. What is easy, what is hard or infeasible? Well, computational complexity of an algorithm gives us an indication. And in general, it's easy if it can be solved in polynomial time as a function of the input. And there's a whole form of analysis of algorithms that analyses and tries to compare which algorithms are hard or easy to solve. And you probably have covered that in some other subjects. Theory of computation and so on. From our perspective, when we say something's infeasible, we mean it's practically impossible. If we try to do that, it will take too long in terms of years to find the answer. Similar to a brute force attack. A brute force attack is theoretically impossible on ciphers, but practically, if we have a large enough key, it would take millions of years, so it's practically impossible. How do we do a brute force attack on public key algorithms? We need to use a key that's large enough to avoid brute force attacks, because in the same way with symmetric key algorithms, if the attacker can, for example, guess the private key, then they've broken the cipher. So the same principles apply. The problem with public key algorithms in practice is that the larger the key that is used, the less efficient they are. That is, the longer they take to do the encryption. So we want a large key to avoid a brute force attack, but we want a small key so that when we encrypt something, it's fast. So there's a trade-off there. And in fact, the practical result of that is that in many cases, public key cryptography is not used so much for encrypting large documents or large plain text. It's more used for key management and signatures, authentication. Because encrypting a 1 megabyte Word document using a public key algorithm and providing the same level of security by encrypting with a symmetric key algorithm, the symmetric key algorithm, like triple DES, will normally be much faster. So generally, symmetric key algorithms for encryption are faster than public key algorithms. So, to attack a public key algorithm, we can do a brute force attack. Try and guess the key, guess the unknown values. But again, we can prevent against that by making the unknown value large. The other way is try and compute the private key from the public key. So we need to choose an algorithm where that's hard to compute. There are no known feasible methods for computing that. Note the spelling mistake here on 5. This requirement 4, given the public key and the ciphertext, it should be hard to find the private key. If there's an algorithm that says, given these two values, here's how you can quickly find the private key, then we don't have a strong public key cipher. So from the attacker's perspective, they can try that, but if an algorithm is secure, then that will take too long. There are another form of attack, a probable message attack. Take all possible plaintext values, that is, encrypt every possible plaintext using the public key, and we'll get every possible ciphertext for that public key. And so let's write this down. You know the public key, PUB here. Take every possible plaintext that there can be, M1 through to MN, encrypt them all, and you get a set of ciphertext values. If you knew the received value of ciphertext, and it matches one of these, then we know the original plaintext. That is, if I've intercepted ciphertext C, I know the public key, I'm trying to find the plaintext message M, I encrypt all possible values of M with the public key, I get a set of ciphertext values. The one that matches this C, let's say it's this one, tells me that the plaintext was M2. I've discovered the plaintext message. Seems easy. Well, how to avoid such an attack? Then make the plaintext long. Ensure that your plaintext is large enough such that it would take too long to encrypt all possible plaintext values. If M is just 4 bits, there are only 16 possible plaintext values. This attack is easy. If M is 1,000 bits, then there are too many plaintext values to encrypt all of them. So we just need to make sure that M is not short. And if we have a short message that we want to encrypt, short plaintext, then we can pad that message out to make it longer. Add some random bits at the end that prevents this attack. So in practice, it's easy to prevent such an attack by making sure that the message you encrypt is long. So that's the coverage of the general requirements of public key cryptography algorithms. Let's see how those requirements are met by RSA, which is one example algorithm and a very popular algorithm for public key cryptography. And the one reason we use it, not because it's popular, and also the algorithm is quite simple to explain and go through. Some of the others are much more complex in terms of the mathematics. So we started on the algorithm last week. We gave some background. The encryption is this equation. The ciphertext equals the plain text raised to the power of E mod n. Decryption, ciphertext raised to the power of D mod n. So we have these three parameters, E, D and N. They make up our keys. Our public key is E and N. Our private key is D and N. The one thing that must be private, secret, is D. So just be careful here. Even though we say the private key is D and N, that's the most common way that we express the private key, N in fact is not private, because the N in the private key is also in the public key. If you know the public key, my public key, then you know my value of N. But you must not know my value of D. That is, that must be kept secret. So to encrypt, we take our plain text, we treat it as an integer, and we perform this operation on it. Some requirements of our input. The plain text input is an integer less than n. So if n is 1023, the plain text message m must be an integer less than that. In practice, we have a block size measured in a number of bits, so that we measure n in terms of a number of bits. So that is, if n, the modulus here, is greater than 2 to the I and less than or equal to 2 to the I plus 1, then we say the block size, m, is I bits. Because if n is greater than 2 to the I, if we choose an m which equals 2 to the I, it will be less than n, which meets our, where do we say that requirement? Here. It meets our requirement that the binary value is less than n. A common value for n we'll see is 1024 bits, but there are other values. If n is 1024 bits, that means our input plaintext message must be an integer less than 2 to the power of 1024, which is a very large number. It makes it, such attack is improbable. Now, what we started to go through was, we went through an example last week of encryption, but we started to go through why does it work, and to derive how do we choose values of E, D and N such that these algorithms work. When I say work, I mean if we encrypt some integer by raising it to the power of E and mod by N, we get our ciphertext. Then when we decrypt by raising that C to the power of D mod by N, we must get the same plaintext back. If we don't, then the algorithm doesn't work. So let's continue going through why this algorithm works, and finally we'll arrive at the requirements for selecting E, D and N. There's our decryption algorithm. Let's substitute in the encryption algorithm. That is, replace C with this equation. This is what we did last week. I replaced C with m to the power of E mod n, all to the power of D mod n, And we can simplify that, bring the d in, so it becomes m to the power of e times d mod n, and the result m to the power of e times d mod n. That is, what did I call it last week? M here is original, and m here was output, or that is, we take our original plain text, raise it to the power of e mod n, and then to decrypt we take that result raised to the power of d mod n, and the output m out, should be the same as m original. So now we have the problem. For what values here does this equation hold? Some number equals that number when we raise it to the power of e times d mod n. And we see some pattern here from, if we apply Euler's theorem, which says the theorem says a to the power of the totient of n plus 1 mod n is equal to a. That's Euler's theorem. Compare them. Same format, same structure. M to the power of something mod n equals m. That's what we have here. M to the power of something mod n equals m. So this is true, that is, these two values of m are the same if it has this structure, because we know this theorem is true, which means e times d should be the totient of n plus 1. That is, some number raised to the power of the totient of n plus 1 mod n equals that number. That's what our Euler's theorem tells us. So for our RSA algorithm to work, this statement must be true. That is, we need to choose values of e, d and n such that this is true. It's not true for all possible values. For example, n equal to 19, totient of n, the totient of 19 is 18. 19 is a prime number, therefore the totient is 1 less. The totient of 19 plus 1 equals 19. If I chose n equal to 19, e equal to 2, and d equal to 5, this obviously doesn't hold. E times d is 10, totient of n plus 1 is 19. That is, if I chose e, d and n as these values, RSA would not work. So for what values does it work? The values such that this holds. I need to choose an e, d and n such that this holds. How do I do that? How do we calculate the totient of some number?
Find the factors of a first.
So one thing that we know, we're going to need these values to be large, especially n. Calculating the totient of a large number is difficult. But we know that the totient of some value n, if n is made up of multiplying prime factors together, that is, if we can factorise n into its primes, then we can easily calculate the totient. Let's recall one of our equations from number theory topic. If n equals p times q, then the totient of n equals the totient of p times q. This is if p and q are prime numbers. That is, we factor n, some number, into its primes. The totient of p times q is the same as the totient of p times the totient of q, which is p minus 1 times q minus 1. If p and q are prime numbers. We'll use that in a moment. What else do we need to know? For what values does this hold? Let's rearrange it or write it in another way. What's the answer? If this is true, E times D mod the totient of n equals if E times D equals the totient of n plus 1, then E times D mod the totient of n equals take the simpler approach. When we mod by the totient of n, it means when we divide by the totient of n, the remainder is the answer. So E times D divided by the totient of n. E times D, which is this, take this side, divide by the totient of n, and look at the remainder. The remainder will be 1, because the totient of n plus 1 divided by the totient of n, the remainder will be 1. There will be 1 left over. Therefore, E times D mod the totient of n equals 1. So we need this to be true for RSA to work. What does this say about our values? E times D mod something equals 1. What's the relationship between E and D? Something times, write it more generally, A times B mod x equals 1. What does this say about A and B? Yes. And another thing we've called it, A is the multiplicative inverse of B. Remember, multiplicative inverse? A times B equals 1 in modular arithmetic means A and B are multiplicative inverses of each other. So E and D need to be, or are multiplicative inverses of each other in mod the totient of n, and E is relatively prime with the totient of n. That is when, so E and D need to be multiplicative inverses of each other. When does a number have a multiplicative inverse? Not all numbers have a multiplicative inverse. A number will have a multiplicative inverse if that number and the modulus are relatively prime. Let's remind you of that. In mod 8, what is the multiplicative inverse of 3? 3. Remember, when we times 3 by something, we get 1 in mod 8. Therefore, the multiplicative inverse turns out to be 3. 3 has a multiplicative inverse because 3 and 8 are relatively prime with each other. Does 2 have a multiplicative inverse in mod 8? No, because 2 and 8 are not relatively prime. The greatest common divisor of 2 and 8 is 2. If they are relatively prime, then the greatest common divisor is 1. So 2 does not have a multiplicative inverse. 4? No, because 4 and 8 are not relatively prime. 5? Are 5 and 8 relatively prime? Yes, they are. Therefore, there is a multiplicative inverse. What is it? I think we've done it before. It's 5, in fact. 5 times 5 is 25. Mod 8 is 1. So, a number has a multiplicative inverse if a number has a multiplicative inverse in mod n if that number and n are relatively prime. Our condition so far is that E times D need to be multiplicative inverses in the mod of totient of n. For that to be true, for E to have a multiplicative inverse, E and the totient of n need to be relatively prime. For this condition to be true, E and the totient of n need to be relatively prime. Because if they are, E has a multiplicative inverse in the totient of n.
And D too.
And D, in fact, yeah, and D as well. But if E has a multiplicative inverse, then D, or if E is relatively prime with the totient of n, then so is D. So, we're almost finished. We need to choose a value of E and a value of n such that the totient of n and E are relatively prime. If we do that, then it means we can find a value of D, where D is the multiplicative inverse of E. If we chose an E and an n such that this was not true, then we would never be able to find a D, and we'd never be able to have values that satisfy our requirements. So if we choose these values appropriately, we can find some D, and then RSA will work. It will successfully encrypt and decrypt. And that leads us to almost to our requirements for RSA. If we ignore the first 3 points and look at how the values of E, D and N are chosen. Choose primes P and Q. Why? Well, we need to choose some value N, E and D. For choosing a value N, we need to be able to calculate its totient. Because if I need to check whether E is relatively prime with a totient of N, I need to be able to calculate this value. Calculating the totient of a large number is impossible, or practically impossible, unless that large number has factors that we know, prime factors that we can calculate. So, what we do, choose two prime numbers, P and Q. N equals the multiplication of those two prime numbers. If that's the case, then the totient of n is P minus 1 times Q minus 1. Easy to calculate. Because the totient of a prime number is P minus 1. The totient of two prime numbers multiplied together is the totient of those individual values multiplied together. So if we choose two prime numbers to create n, then we can easily find the totient of n. So we choose two prime numbers, P and Q, calculate n, easy, multiply two numbers together, that's an easy operation. Find the totient of n, that's easy. Choose a value of E as less than the totient of n that is relatively prime with the totient of n. That is such that this is true, which is the equation that we have here. Choose P and Q, we have n. We have the totient of n. Now choose an E which is relatively prime with the totient of n, and there are algorithms for doing that, quite easy. And now we have E, n, the totient of n, find D. Find E's multiplicative inverse. And again, there are algorithms for finding that. And we now have our values of n, E and D. And we know that RSA will work if we use those values. That is, if we encrypt some message raised to the power of E times D mod by n, we will get that original message out. Hence, we have the algorithm for choosing keys or generating keys in RSA. Choose two primes, multiply them together, calculate the totient of n, find E, which is relatively prime with the totient of n, and then find D, which is the multiplicative inverse of E in the totient of n, in the mod the totient of n. And the result is that n and E are public key, D and n are the private key, and perhaps most importantly, D must be private, secret, so must P and Q. We'll see why in a moment. So n and E can be made public, P, Q and D should be private in this algorithm. Let's give an example to show how those keys are generated and return to our encryption. So we've arrived at how to generate the keys such that RSA will work. Let's illustrate how to generate keys. I choose two prime numbers. For RSA to be secure, these prime numbers need to be large. So the example I'm going through is not secure. That is, we can do an attack on it easily, but we can do it on the board. I choose two prime numbers. I want to generate my pair of keys. Everyone else would do the same to generate their own pair of keys. Choose two prime numbers. N equals the multiplication of those two prime numbers, 17 times 11, 187. The totient of 187 equals 16 times 10, according to this equation. Because they're prime numbers, the totient of the multiplication of those two equals P minus 1 times Q minus 1, 16 times 10. Easily, I've found n and the totient of n. Now the next step, choose E, such that E is relatively prime with 160. Find a value. Find a smaller value. Choose E. That should work. 79, will that work? No. The requirement is that E should be relatively prime with the totient of n. That is, E, the value that you choose, should be relatively prime with 160. Which means that the greatest common divisor of those two is 1. There are multiple values where that is true. So there are multiple values of E that we can choose. I'm going to choose 7 because I have the answers. And there are algorithms for doing that. When we have large numbers, there are algorithms that do that efficiently. 7, let's check, is 7 relatively prime with 160? What are the common divisors, or what are the divisors of 7? 1 and 7. And the divisors of 160, what's common? Well, the only common one is 1. 7 is not a divisor of 160, and therefore E equals 7 and 160 are relatively prime. There are other values that are acceptable. Now calculate D, where D is the multiplicative inverse of E. Find D. The reason I chose E is equal to 7 is because it's easy to find D, which you're going to do right now. Find D. E times something equals 1, mod the totient of n.
100 equal. No. Getอะไรได้106.
Have an answer? 23. 7 times 23 equals... So, what's our requirement? E times some number mod the totient of n. That's our requirement. We want to find the multiplicative inverse of E, 7. Seven times some number, mod 160 equals 1. A simpler way to do it. And in fact, we find the answer straight away. 7 times some number equals 161, because 161 mod 160 equals 1. Or if that doesn't give us the answer, it does in fact, if it doesn't, 7 times some number equals 321, because 321 mod 160 is also 1. Or 7 times some number equals 481, because 481 mod 160 is 1. In this case, 7 times 23. 7 times 23 is 161. Therefore, D equals 23. We didn't have to try other steps. In your quiz tomorrow, if you need to solve this, then you may have to try multiple steps. That is, if there's no such answer, no integer, when we multiply by E that gives us, in this case, 161, then try the next step. 7 times some number should equal 321, and so on. That's a way to quickly do it, at least on a piece of paper. Find some number. D, when we multiply by E, we get 1 when we mod by the totient of n. We didn't have to do that this time because it was easy. We have our keys. We've generated our pairs of keys. We have chosen 2 prime numbers, P and Q, calculated n to be 187, prime 17 and 11. Calculating the totient of 187 is easy. Because they are primes, we get 160. We chose a value of E. There are multiple to choose from. So long as it was relatively prime with the totient of n, with 160, I chose 7. And then we calculated D such that 7 times D equals 1, mod 160. And it turns out D equal to 23 satisfies that. So we have E, D, and N. My public key that I just generated is the pair 7 and 187. The private key is the pair 23 and 187. The things I will not tell you that must be kept secret to me are 23, D, that's private to me, and P and Q. I should not tell you what P and Q were, because an attacker, if they know P and Q, can break RSA. And now I would use those keys to do encryption. Go back a step. Now I've got a key pair. You want to send something to me confidentially, you would use my public key. You would take your plaintext M raised to the power of 7, my value of E, mod by 187, and you'd get the ciphertext. You would send me the ciphertext. I would take the received ciphertext, C, raised to the power of 23, my private key, or my private D, mod by 187, and I'll get the original plaintext back. And that will work for sure because of the ways that we've chosen E, D, and N.
What PU and PR stand for?
PU, public key, PR, private key.
Public key. Why not U and R come from
PU, public, PR, private.
Okay.
We can't use P on its own,
Okay.
so a common way is PU, PR. In symmetric key ciphers, you'll see K, because you use the same key at both sides.
You should add K after that. I understand.
Sometimes you'll see PUK, PRK as well. That's okay. It's just the notation I will use, and you'll see various notations. In fact, you'll also see the subscript to say that it belongs to a certain user. PUB, PRB belong to user B. So what we've done, we made sure that we could have values of E, D, and N such that this equation held. M to the power of E, D mod N equals M. That is over here. We went through the steps to derive E, D, and N. And in fact, now, when you generate your keys, you just follow the steps here. It needs to be easy to calculate M to the power of E mod N and C to the power of D mod N for all possible values of plain text. And it should be hard to determine D given E and N. That is, for the attacker, for this to be secure, it should be hard for the attacker to find D, the private key, from D and N, from E and N. We'll go through the attacks that the attacker can try in a moment. And our requirement was that E and D are relatively prime, though multiplicative inverses of each other. And we got this algorithm for generating the keys. And the entire RSA algorithm is summarized here. The key generation steps from some user, Alice in this example. Select two primes, P and Q. They shouldn't be the same primes. Calculate N as P times Q. That's simple or easy to perform, even when we use large numbers. If P and Q are hundreds of bits in length, still multiplying them together can be performed quickly by a computer. calculate the totient of n as p minus 1 times q minus 1. Again, that's easy to calculate with a computer. Select some integer e such that it's relatively prime with the totient of n. That is, the greatest common divisor of the totient of n and e are 1. Again, there is an algorithm for calculating that. Calculate d, which is the multiplicative inverse of e in mod the totient of n, and we have our two keys, our public key and private key. So every user in the system, all of you, when you want to use public key cryptography, you need your own pair of keys. You would go through these steps and find your public key and your private key. You can then tell everyone your public key, your values of e and n, but you cannot tell anyone your value of d. Again, the private key we say is made up of d and n, but n is not secret because n is also in the public key. To encrypt, for confidentiality, Bob takes Alice's public key, takes a plaintext m, some integer, must be less than n that we have up the top, and takes m, raises it to the power of Alice's e, mod by n. We get the ciphertext. When Alice receives that ciphertext, she takes her private d, c to the power of d, mod n, and gets the original plaintext back. So RSA, the encryption and decryption algorithms are mathematically very simple and can be implemented quite easily. Although compared to symmetric key ciphers, that takes a long time to calculate when we have very large numbers. But it's possible. You should know those steps of how to do the key generation and encryption and decryption. The next thing we're going to do, there's an example there that we're not going to go through, but it shows similar to the example we used last week to encrypt and decrypt. Raise our plaintext to the power of e, mod n, get the ciphertext. Ciphertext raised to the power of d, mod n, gives us our original plaintext. You're going to try that on different values. And see that the plaintext here, m out, is always the same as the original plaintext, m orig, because of the way we chose e, d, and n. What if we have a large plaintext? Then again we can break it into blocks and apply RSA on blocks. There are different ways to do it. That's one example of how to do it, but we won't go through that. That is the same way that we use modes of operation for our symmetric block ciphers. If we have a large plaintext, we break it into blocks, and we can do the same with RSA. What we want to do now is to show how the attacker can try to defeat RSA. So I'll come back to the algorithm here, and we'll show on the board 3 different ways that the attacker could attempt to try to break the security of RSA. Before we do that, any questions? Quiz tomorrow has a question on RSA. You need to solve some problem. Any questions about the steps for doing the key generation, generating E, N, and D, and doing the encryption and decryption? you should be able to...
How many techniques do we have to remember?
Sorry?
How many techniques do we have to remember for the quiz tomorrow? Because there are several techniques.
Well, we've said already that there's a question on RSA. That's one thing you need to know. What else did I say? For those people who arrived late, I said there'll be something about meet in the middle attack. So there's 2 hints. And there'll be at least one other question. Any other questions before we attack RSA? Is that a question? If we use, with RSA, it turns out if we encrypt with the public key, we can only decrypt with the private key, and the same in the other way. If we encrypt with the private key, we can only decrypt with the public key. That is, what's the difference between E and D? The difference between the public key and the private key is that PU has E, PR has D. When we went through the generation, we had E times D equals 1, mod the totient of n. We chose E, and we found the multiplicative inverse of E to be D. And it's the same the other way. If we just rotate E and D, we get the same properties are met. So if I choose D and find its multiplicative inverse, I get E, which is just the same values. So we can use them, if that's your question, we can use them in both directions because our requirements for generating them are still met.
So does RSA provide both secrecy and authentication?
So we can use RSA to provide secrecy by encrypting with the destination's public key, or we can use it to provide authentication by encrypting with the source's private key. So it works with RSA in both ways. It doesn't work for some other algorithms. Yeah.
Everyone knows the public key, right?
Yep.
Why isn't it the same? I mean, work backwards to...
Why does...
I mean, if you know the public key is needed, you should be able to work backwards together. Plain text.
If you know the public key, let's try and get this clear. If you know the public key, you want to... your question is about why does it work, or...
Why we, let's see.
No, let's get it clear, because I'm sure there's other people that understand less as well. So it's worth explaining. We have time.
If I have a public key to encrypt, I mean that it should, for the attacker, it should be able to use the public key to decrypt it as well.
If we go back to one of our earlier slides, recap, it's a long way back. This one covers it. Our general requirement for public key encryption was we have some algorithm. If we encrypt our plaintext X with a public key, we can take the ciphertext that we generate, Y, and with some decryption algorithm, we should get we must be able to get the original plaintext X if we decrypt using the different key PR, or the private key in this case. Why does that work? Well, for RSA, the way that we chose those algorithms and the way that we generated those values of E, D, and N made sure that it would work. Can we give another example on the board? Well, what we ended up with was, we called it M original, or M. The way that we generate the values of E, D, and N is such that the value output here, when we decrypt the ciphertext, equals the value input here when we encrypt the original message. Now, I think your question is not about that, but about now what the attacker can do. Is that right? This is what the steps we've gone through this morning, and even we started, in fact, on yesterday. That's those detailed steps. That showed that RSA could decrypt and get the original plaintext back.
It's okay.
Okay, all right. You're asking a question about what I'm about to cover now. So you're asking about what the attacker can do to break this. Let's go through that. That is another question. Yeah. Okay. Yeah.
What actually is confidentiality, because you said that it's secrecy and authentication?
Secrecy and confidentiality are the same in this case. Secrecy, we want to keep the message secret, private, confidential. So often the words secret, private, and confidential are used to mean the same thing there. So when I say secrecy here, I mean confidentiality. Maybe it's better to think as confidentiality, because sometimes we confuse secrecy with other things, and same with privacy. So, you're the attacker. You know the algorithm. What else do you know? We want to see what the attacker can do to try to break RSA. They know the algorithm. They know N. They know E. And what else do we assume the attacker knows? We have the public key, E and N, and the ciphertext. That is, if I've just sent something that... So what I did, if we've got A and B and the attacker, A has taken their message and they've sent the ciphertext, which equals M to the power of E mod N. B, where E is the public key of B, and B can decrypt that. But the attacker intercepted. The attacker knows, of course, the algorithm that's used, all the steps here. They know C, the ciphertext that was received, and they know the public key of the recipient, B. That is N and E, because they are public. What do they not know, or what do they want to find? D and or M. If I find the message, then we don't have confidentiality in this case. So that's one objective, and ideally the objective is to find D. Find the private key, or find D as part of the private key. The private key, the value of N is already known, so the only thing secret is D. What are the steps that we can follow to do that from the attacker's perspective? Let's try and first find M. To find M, let's look at the equations that we have. We know the equation C equals m to the power of e mod n. So here's an equation. What are the knowns in this equation? It has 4 variables, C, m, e, and n. What are the knowns? C, E. An equation with 4 variables, 3 knowns, easy to solve. Normally easy to solve, but not this equation. Why? They want to find m, given that they know C, E, and n. How do you find m? What operation does it involve?
Try all possible.
Okay, brute force attack. Try all possible m's, but with, yeah, that's one approach. That's a brute force attack. Try all m's, but m is, if it's large enough, then all possible values of m will be too large to try them all. So one requirement is that m is long. Maybe if m is 1,000 bits, then trying all possible values of m will take you forever. So a brute force attack will not work if m is large enough. So what else can we do if we don't try a brute force attack? From this equation, this is the first attempt. How do we solve this equation? What's the operation that we know that gives us the solution? Logarithm. Well, we've got an exponential in mod n. The inverse, we really just need to find the inverse. The inverse of an exponential is a logarithm. In mod n, we call it a discrete logarithm. Discrete log in base m. So the base is m. The modulus is n of c equals e. That's another way to write this. The discrete log in base m with mod n of c should be equal to e, the exponent. It turns out that's hard to solve. That is, in fact, here we need to find m. Given some c, given the modulus n and the exponent e, find the base where this is true. Solving discrete logarithms for large numbers is computationally hard, practically impossible. If you recall back to the end slide on number theory, we listed 3 problems which were computationally hard. One of them is solving discrete logarithms. So, mathematically, the attacker needs to solve a discrete logarithm. If the values are large enough, then that's practically impossible to do. So, this approach of finding m, the plain text, is not possible if we choose large enough values, especially for n here, and large m. If n is large and m is large, then a brute force is not possible on the message, and solving a discrete logarithm is not possible. So that approach fails. What else can the attacker do? What was our objectives? Find D or M. We just tried finding M. Didn't work. That didn't work. Let's try a different approach. So that approach will work with the numbers that we used in our example. In our example where we used n was 187, we had e was 7 and d was 23. If we applied this approach, if someone encrypted some message which was less than 187, we could solve it and break RSA. So it's possible if we use small values. It's quite easy to solve. You could manually do it, you could use a computer to solve that. But if you use large values, that's not possible. That's the point there. Find D is the other approach. How do we find D? Actually, there's two different approaches. Let's look what we know about E and D and N. We know E, the relationship between E, D and N is given by this equation. E times D mod the totient of N equals 1. That's the way that they were chosen. E and D are multiplicative inverses in mod the totient of N, which is really written as D equals E to the minus 1 mod the totient of N here. It's the same meaning there. E and D are inverses, multiplicative inverses. So we know that, or the attacker knows that. What's known? E is known. N is known. D is unknown. D we're trying to find as the attacker. So again, we have an equation with 3 variables, 2 known, 1 unknown. How do we solve it? What's the totient of N? How do we find that? Or in general, how do we find the totient of some number?
Find a factor of 1 plus of n first and then by a table.
Okay. What's the totient of 34, for example? No, 34 is not prime. N is not prime. All right. What's the approach for finding it? Look at the numbers less than 34 and look at which ones are relatively prime with 34. 1 and 34, yes. 2 and 34, not relatively prime. 3 and 34, yes. 4, no, because 2 is a divisor of 4 and also of 34. 5 and 34. So we'd go through and test all those numbers up until 33. That's possible, but it's not possible when this number is large. This is our value of n. When n is large, again, say a 1,000-bit number, it's a very large number, there's no known algorithm that will find the totient of it using this approach. So the attacker, if they know n, they cannot find the totient of n using this manual approach because it will take too long if n is large enough. Again, in our example, we used n was 187. I could give you a quiz tomorrow and say, find the totient of 187, and you'd spend 30 minutes and you'd find it. 30 minutes, okay. Or you'd write a computer program, it will find it in a few seconds, okay? But if n is now 2 to the power of 1,000, a very large number, then your computer program will take millions of years to find it, okay? So the attacker cannot manually solve the totient of n. This approach will not work. So what do they do? Yeah. N, in fact, came from P times Q. If the attacker knows P and Q, they will find the totient of n quickly. The same way that the person who generated the keys found the totient of n, if we know P and Q, we can immediately find the totient of n as simply P minus 1 times Q minus 1. So now the problem for the attacker, given n, a large number, find its 2 prime factors. And it turns out again that this problem is also computationally hard. Taking a large number, finding its prime factors is going to take too long, so long as n is large. Again, a 1,000-bit number should be large enough. So from the attacker's perspective, there are 3 approaches. First approach, find the plain text m. Well, to do that, we need to solve a discrete logarithm. For large numbers, discrete logarithms are computationally infeasible. We cannot solve them for large numbers. Another approach, manually find the totient of n. And again, for large values of n, there is no known algorithm that can find the totient of it in this manual approach without knowing the prime factors. So that's not feasible with large values. Finally, find the prime factors of n, and then we can easily find the totient of n. Factoring large numbers into their primes is again computationally infeasible if n is large enough. And that's the three problems that we listed, I think, at the end of the number theory slides. As a result, if we use large enough values, RSA is considered secure because the attacker cannot find D or M.
The freeway is ways to solve this with logarithm. The second is to tertial event, and the third is to factor it in.
Yes. First approach, to solve the discrete logarithm. Second approach, solve Euler's totient, calculate Euler's totient of a large number. Third approach, factor n into its prime factors. All three are computationally infeasible with large enough numbers. And it turns out that people think that the easiest of those three problems is factoring. That is, with large numbers, this will take equal to or less time than these two approaches. Therefore, the security of RSA is generally measured by how large n is and how easy it is to factor. Because if this is the easiest approach, then that's the one that an attacker would use to break it. The others are considered harder. That is, that'd take not 1 million years, but 10 million years. So take the easier approach. How hard is hard? That's the question. How large a number do we need for these problems to be hard? Some examples. We'll come back to the efficiency in a moment. The security of RSA, brute force attack, try all values of M, try all values of D. Of course, that's possible. Just make the values large enough, and a brute force attack is infeasible. Mathematical attacks, those three approaches that we just listed there. Factor n into its primes, determine the totient of n directly, determine D directly without determining the totient of n. We've missed one. How can we write it as an equation? If we can find the value of D without finding the totient of n, that's another approach. From our encryption algorithm, we see the relationship there. If we can find D from this, then that's another approach. But again, we don't have... If we can find D, then we've also broken RSA. But we don't have our plain text in this approach. But if we have a pair of ciphertext, plain text, we do. That is, this is our decryption algorithm. I know n. I have intercepted a ciphertext, and in the past, that ciphertext was in the past, and I've recently found out what the corresponding plaintext M was. So I know a pair of plaintext ciphertext, M and C. I want to find D. Again, solve this equation. It's our discrete logarithm. So discrete logarithm, prime factors, determine the totient. All too hard. Let's finish on how hard different values of n are. The company that developed RSA is a company as well as an algorithm, used to have a competition where there was a large prize of $100,000, for example, if you could factor a number of some length into its primes. And this is a bit old now, but there's some more details on the website, but we'll see that this is the first column is the length of the value of n in decimal digits, and the second is the approximate number of bits. And this is the time when people found a solution. That is, given a 100-digit value of n, in 1991, people found some algorithms to factor that into its primes. And they improved over time, and in 2005, people could factor a 663-bit number into its prime factors. So n, if it was 663 bits long, then they could factor it at that point in time. And recently, or not recently, several years ago, RSA 768, that is a 768-bit value of n, was factored. How long did it take? On the website, the RSA 768, I think it says on here. So there was a 768-bit number. In 2009, some people found the factors, the two values of P and Q. It took the effort of almost 2.2 gigahertz CPU years, which in calendar time it took about 3 years to factor. So there's a 768-bit number. It took about 3 years to factor into its primes. So increasing up to a 1,000-bit number is still going to be very secure because it's going to take too long, even with much faster computers. This is with 2,000 different CPUs. They are the two prime factors, P and Q. There. So we just need a value of n which is large. 1,024 bits is recommended. Sometimes people use 2,048 bits, which are not considered, it's not considered that they can be factored in any time in the near future. Unless someone comes up with a new algorithm, which is no known algorithm at the moment that can factor them faster than what they have. Did that answer your question about how the attacker can defeat RSA? Did that answer your question?
Yes, already.
Already? Have we missed anything? So that's about the security of RSA. As the users, we need to be able to quickly perform calculations with RSA, generate the keys quickly, do the encryption and decryption quickly. Some comments about what's easy, or some typical values to be used to make sure RSA is efficient in terms of performance. Even though we use very large numbers, and we do exponentiation, that is c to the power of some large number to the power of some other large number, we get a very, very, very large number. We can use these properties to make those calculations faster, this modular arithmetic properties. So it's feasible to implement in a short amount of time. How do you choose a value of E? There are some recommended values that suit for most values, so 3, 17, 655, 37. You can use larger values or other values, but these generally make the implementation faster. using a small value is a problem if we don't use some padding on the plain text. But again, it's overcome by using padding. Small values of D are vulnerable to attack. Someone can guess it. There are algorithms for making the decryption fast when we have large values of D. So again, there are algorithms available to make the implementations fast enough to be used today, even when we're using large numbers. How do we choose P and Q? Choose two large prime numbers. They need to be very large because when we multiply them together, we need to get a 1000-bit number, n. So P and Q need to be large. The approach that is used is to really choose two large odd numbers which are random and check whether they're prime. There's no easy way to select a large prime number. So the approach is to test if it is prime. And most cases, if you do enough tests to check if it's prime and you find that it's not composite, then you assume it's prime. So again, there are ways to do that. And that, I think, finishes on RSA. What we'll go through next is another public key algorithm, but it's not used for confidentiality. It's not used for authentication. It's used just for key exchange. Exchanging a secret such that no one else knows the secret. So two users want to exchange some secret value. We don't want anyone else to know the secret, but we want to exchange that secret in a public network. We'll see that Diffie-Hellman does that for us. But we will not start that today. We'll start that tomorrow. We'll finish our lecture there, and tomorrow we'll